Okay, looks like I took out my the so let's redo which one. This one. And I'll replace it.
Okay.
Okay, welcome back. About time to get started. Before we launch into the lecture, there's just a few announcements I probably should make. First of all, this coming Monday, so almost not quite a week from now, is a GRCC holiday for Independence Day, but what classes do meet on Tuesday. So for this course, there's no break for the holiday. If you're planning on traveling, then you should just be aware of that. Of course, you can connect with the course at a distance. So if you want to attend the lecture by Zoom or submit your papers by email, that's okay to do. It's already set up. So, but just to make you aware, we don't get any days off. There is a homework 8 that has already been posted. And that is, well, what I really wanted to do was to make it due on Thursday. But I'm aware of the fact that there's not very much time between Tuesday and Thursday. So what I actually did is make it due on Friday. So if you want to turn it in person in class, then of course you need to do that on this week, Thursday, but you're welcome to email to me through Friday. I am aware of the fact that that's kind of squeezing into the holiday weekend. But on the other hand, we have our second exam on Thursday, July 15th. So that's not much more than 2 weeks from now. So if I slack off a little bit, I know what happens. People get behind, and so the assignment for Thursday is not very long. I think it's about a half a dozen problems from each of 2 sections, and those 2 sections we're doing tonight. And they're not especially difficult. They take a little bit of work, but I think you'll be able to get them worked out. If you do need a little bit longer, so they come in on Friday, that's fine. I can't think of anything else I need to draw your attention to right now other than the lectures. So I'm ready to start unless someone has a question about scheduling or other things before we launch into the material. Okay, well, let's start with 2.8 then. This is on the solution of non-homogeneous equations. This handout honestly doesn't have very much in the way of blanks to fill in, so I think I'll just leave this as kind of a standalone document, and I will do the lecture basically as a series of examples with a little bit of explanation as we go through them. So let's start out with this one right here. Example 1 is y double prime plus y prime minus 6y equals 21 e to the minus 5t. So the thing that's new, of course, is I have something other than 0 on the right-hand side. We already know what to do if you have a 0 on the right-hand side. This has constant coefficients, so you'd switch over to the quadratic equation. That's the characteristic equation here, lambda squared plus lambda minus 6y, and we're actually going to need it. So let's go ahead and write that down. And in this case, the characteristic equation is easily factorable. We have lambda plus 3, lambda minus 2 equals 0. And that tells us that lambda could be either minus 3 or plus 2. And so the solution to the homogeneous equation is C1 e to the minus 3t plus C2 e to the plus 2t. Now, the reason we need that first is that every time we do this, the method we're about to describe here, which is called the method of undetermined coefficients, you want to check to see whether the thing you're after falls inside of the homogeneous solution. It doesn't in this case. E to the minus 5t is what we really care about. The 21 we'll deal with it as we go along. But e to the minus 5t does not appear here, so we're good to go. This is the simple case. So what we do is we reason in the following way. We only have constant coefficients here. So there are certain types of functions, exponentials are among them. If you take a derivative or a second derivative and multiply it by a constant, you get that same kind of function back. So if I start with anything times e to the minus 5t, multiply by a constant, add its first derivative, add its second derivative, I'm going to have something involving e to the minus 5t at the end, right? And as a matter of fact, just by taking derivatives and adding up terms like this, the only thing that could possibly give me an e to the minus 5t after it runs the y, after it runs through the left-hand side, is something like this. So what we say is a particular solution must have this form. It must be some constant times e to the minus 5t. And we can figure out what constant it is. So this is in the undetermined coefficients name. This is the undetermined coefficient. We don't know what coefficient we need on this function, but we know we need this function. So then we just write down what its first and second derivatives look like. Well, every time we take a derivative, a chain rule factor pops out, but that is it. It's pretty simple in this case. Minus 5, e to the minus 5t is the first derivative. And the second derivative is plus 25a, e to the minus 5t. So up to a single constant, we know what yp must be, and we know what its first and second derivative must be. So we're going to plug them into the left-hand side. So y double prime plus y prime minus 6y equals, well, y double prime is 25a. I'm not going to write that exponential every time. I'm going to cover that with some parentheses in a minute. 25a e to the minus 5t plus y prime, that's minus 5a e to the minus 5t. And then minus 6 times yp will be minus 6a. Everything has e to the minus 5t on it. And when I add those all up, I'm supposed to get the right-hand side of 21 e to the minus 5t. Okay, well, let's see, 25 minus 11, 14a e to the minus 5t equals 21 e to the minus 5a. So we just have to solve this one linear equation here. A is equal to 21 over 14. Divide up and down by 7, we get 3/2. Therefore, a particular solution to this ODE is 3/2 e to the minus 5t. Now, I talked through it pretty rapidly a couple of sessions ago, so let me say it again. For linear ordinary differential equations, if you can find the general solution to the homogeneous equation, call it YH, and we can in this case, it's C1 e to the minus 5t, whoops, 3t, minus 3t, plus C2 e to the 2t. So if you can find the general solution to the homogeneous equation, and you can find any solution at all that solves the non-homogeneous equation, and we just did, this one will solve that equation, then the sum is the general solution of the original ODE. So it's 3/2 e to the minus 5t plus C1 e to the minus 3t plus C2 e to the 2t. And that is all possible solutions of this original ODE right here. Second order linear. Means you're always going to get a solution that looks like this. Y equals some particular solution plus C1 times some basis function for the set of solutions of the homogeneous equation plus C2 times some linearly independent function compared to Y1 of that homogeneous equation as well. So this part here is the YH, and this, of course, is the YP. This will always happen with second order linears, whether you have constant coefficients or not. Now, in this case, we do, and that's good. It really simplifies things. But even if you don't, this is still a true statement. Now, if you notice, we did first order linear as our very first special case. And we said in that case, y is equal to, let's see, e to the minus h times integral e to the h r dx or dt, depending on whatever your independent variable is. And if you expand that, what you've got is some kind of a function that involves a little bit of work to get. That's this thing right here, plus a constant times some other function. And the h is some antiderivative of the p. So notice this would be just y1 in this case, and this would be your yp. So for first order equation, you're going to get a yp plus one constant times one basis function for the first order linear solution space of the homogeneous equation. Second order equation, C1y1 plus C2y2. Had we solved a third order equation, you can probably guess, you'd have a particular solution plus C1y1 plus C2y2 plus C3y3 and et cetera. It's going to go that way for nth order linear equations. Now, the good news is that sort of the classical equations of mathematical physics are all collected in the first and second order. So that's really what we pay attention to in this course. However, there are some higher order equations that do come up in practical engineering. I think, for instance, bending of a beam involves a fourth order ordinary linear differential equation, but it's kind of a rare case. There aren't that many. Most of them are first or second order. So anyway, just be aware of this pattern here, because for the rest of the time we work on linear differential equations, you're going to bump into it every time. So just starting here now, at this point, with what little bit we know now is, well, it's second order linear. We see constant coefficients. We see an exponential right-hand side. And so that means you know ahead of time that you're going to have this kind of a pattern right here, a yp plus a linear combination of two basis functions for the homogeneous equation. Then, with a little bit of extra work, you can generate the you can generate the homogeneous equation, and then you notice that this function, e to the minus 5t, does not land on either one of these. So that means you've got a relatively easy case. You can guess the form. You run it through the left-hand side of the equation, set the undetermined coefficient to be what it needs to be in order to get your desired right-hand side, and you're done. Okay, so that's the first example, and Now I wanted to show you another one that's like it. So for example 2, and what I'm actually doing is kind of running through the catalog of right-hand sides for which YP is guessable. So last time I had an exponential function on the right-hand side. This time I have a polynomial, and it's only degree 2, thank goodness, because it's going to have enough terms in it as it stands. Now, if you start taking polynomials and you take one or more derivatives, the degree is only going to go down, right? So if we're trying to generate a second degree polynomial on the right-hand side, then first of all, only a polynomial could create that. Exponentials, cosines, sines, sinh, cosh, logarithms, none of that stuff would be of any help in trying to get the polynomial function on the right-hand side. So we know that a particular solution must be of this form. It's got to be polynomial, but even more than that, it can't have degree higher than 2. And here's why. Notice that if you had a third degree polynomial, this minus 6y would have an x cubed term on it, right? But there wouldn't be one here, and there wouldn't be one here, so that x cubed term would not cancel out, and it would appear on the right-hand side. So x cubed is out, x to the 4th is out, x to the 5th is out. The only things that could possibly work are second degree terms, first degree term, and a constant term. So we can guess its form. And of course, this is the same left-hand side that I had before. So we can just copy our YH from previously. It's C1e to the minus 3t plus C2e to the plus 2t. And clearly, this function is not colliding with this one. There's no interaction between those, and that's good. You'll see what I mean in a little bit about that, but I'll give you an example where they do collide, and it's a little bit harder to solve, but not actually too bad. Okay, so if our particular solution is of the form ax squared plus bx plus c, then we know the first derivative would be 2ax plus b, and the second derivative is 2a. And then we can substitute this into the left-hand side. Now, I'm writing the left-hand side out here because I'm trying to produce reasonable notes. But of course, if you're just solving the equation, you may or may not even write down yp and yp prime and double prime, because in this case they're so simple. But eventually you got to write what comes here, and that part really is essential. So y double prime is 2a, and I'm going to put parentheses around here, not because you need them, just so that you'll be able to look at the notes later and figure out what's going on. Y prime is 2ax plus b. And minus 6y is the next piece. And actually, it would have been better had I put the minus 6 out here. Minus 6 times ax squared plus bx plus c. And all of that is eventually going to have to add up to 6x squared minus 2x. Okay, well, 2a plus b plus 2ax, there's another linear term here, minus 6bx. And let me see, our only quadratic term is minus 6ax squared. So if you want to really dot all the i's and cross all the t's, then I suppose you would write it like this. And this has to be equal to the right-hand side of the ODE, 6x squared minus 2x. So we now have a system of equations. The constant term on the right-hand side, I could put that down here if it helps, plus 0. So the constant term on the right-hand side is 0. The constant term on the left-hand side is 2a plus b. So it must be, nope, it's not. I know there's another one. Minus 6c should be in there, right? Where'd it go? I think I just lost it. So right here, minus 6c. Okay, now we equate coefficients. So the constant term on the left side, 2a plus b minus 6c must be equal to the one on the right, which is 0. The first degree term on the left is 2a minus 6b, and that must be equal to minus 2. And the second degree term on the left-hand side is minus 6a, x squared equals 6x squared equals 6. So from this, I can see that a is equal to minus 1. And once I know that a is equal to minus 1, then I'll have minus 2 here equals minus 6b equals minus 2. Well, the minus 2 and the minus 2 add out, and b is equal to 0. And once I know that a is minus 2, so I got minus 2 here and 0 here, so 6c equals minus 2, and therefore c equals minus 1/3. Jeffrey, I see you pondering that. Is there a question, or is there a part that doesn't quite fit for you? Or did I make a mistake? You know,
I'm just mostly wondering why b equals 0. But...
Oh, okay. Well, let me just write out the details. First of all, I determined from here that a is minus 1. So 2 times, got it? 2 times minus 1 plus b equals minus 2. So that's minus 2. And b equals 0 is the solution. I'm doing back substitution. Remember when we did that way back with systems of equations? If I wrote this out in a nice form, in a rectangular form, it would be lower triangular, I think. Minus 6a, let me write it with the variables so I don't get confused, equals 6. This one is 2a minus 6b equals minus 2. And this one is 2a plus b minus 6c equals 0. So I have a lower triangular system. So I started with the a, that allows me to get b, and that allows me to get c. And there's no reason you have to do it this way. Another perfectly valid option is you could write that as a matrix equation and plug it into calculator, right? And it won't make arithmetic errors while it's solving the equation. Now, you might make an arithmetic error getting it from here into the calculator. I've certainly typed things in incorrectly before, but you know, it's a reasonable thing to do as well. And some of these, you know, some of these do get kind of messy. So there are reasons that you might want to use technology to at this step. Okay, well, we now know why the particular solution yp is. We've determined that a is minus 1, so that's minus x squared. B is 0. I'll I'll write this just once. And C is minus a third. So there's YP. We already had YH, that is up here. Linear combinations of e to the minus 3t and e to the 2t. So the general solution is the particular solution plus a linear combination of the two independent solutions to the homogeneous equation. And once again, we have that form. This is YP, and that's the general solution to the homogeneous equation. There's YH. So what we've seen so far is this. If you have an exponential function on the right-hand side, and it doesn't overlap with a homogeneous solution, you guess a general form for that exponential, run it through the left-hand side, figure out what the coefficient must be, and that gives you your YP, and then you add YH, and you're done. Option 2, you might possibly have a polynomial over here. Well, you take a polynomial of the same degree with unknown coefficients, run it through the left-hand side of the equation. It's going to be kind of messy, probably, but even though it's not easy in the sense that it takes time, and you got to be careful of the details. It's not sophisticated. So you run that through the left-hand side, and then you solve for all the coefficients. That gives you YP. You add it to YH, and you're done. There are a couple of other classes of equations that will work out that way. Another one would be sine and or cosine. So let me pick one of those. Y double prime. So I suppose I should label this. This is example 3. Y double prime. Now, by the way, this works with other second order linear ODEs with constant coefficients. I'm repeating the same left-hand side because it saves me the time of computing the homogeneous equation, or the homogeneous solution time after time. Okay, so let's put 12 cosine 2x, 2t on the right-hand side. We have already done this so that we know YH is C1 e to the minus 3t plus C2 e to the plus 2t. And there's no overlap between cosine 2t and either of these. So now we have to guess what form would the particular solution have. Okay, so let's just think about this. When you start with cosines and you take two derivatives, what kind of functions will you see? You'll see a sine. What happens if you take the derivative of that? Yep, you bounce back to the cosine, right? So sine and cosine, and we're only dealing with one argument here, it's 2t. So our particular solution may need to have a cosine term in it, and it may need to have a sine term in it, but that's all that could be needed. There is nothing else you could take a derivative of and come up with cosines. And if you start with sine and cosine, and you take a couple of derivatives, multiply by constants, add the whole mess up, you're only going to end up with cosines of 2t and sines of 2t, right? So this is a closed system, is the idea. And so we know that it's got to have that form. Well, the first and second derivatives are kind of messy in this case. They're not as bad as they might be, but they're getting worse. Okay, now if I take the first derivative here, when you take the derivative of cosine, a minus pops out, and then you get a chain rule factor of 2. So minus 2a sine of 2t. But when you take the derivative of the sine, you don't get a minus. However, you do get a chain rule factor of 2. And when you take the second derivative, well, you'll just wrap around to the original functions. Sine, cosine, then back to cosine, and sine, cosine, back to sine. But you'll have 2 chain rule factors, and you will definitely have a negative on both of them. So minus 4a cosine 2t plus, minus 4b sine 2t. And now we got to put this in the left-hand side. I'm going to need every inch I can get here, I think. So I'm going to cheat and go all the way over to the margin, which I'm sure is breaking some rule of English composition, but you know, the English department isn't watching right now, so we're okay. Oh, they are. They're just terribly polite.
Well, it's fine.
I had forgotten. That wasn't a big build-up to a joke. Okay, y double prime is here. Then I need plus y prime. Oh my goodness. Minus 2a sine 2t plus 2b cosine 2t. Then minus 6 times the original yp. So minus 6a cosine 2t minus 6b sine 2t. Oh. And if ever we've written an expression in here that needs simplifying, this would be it, right? So I'm going to try to find all the cosines, I guess, first. Here's a cosine. Here's a cosine. And here's a cosine. So I've got minus 4a, minus 6a makes minus 10a, plus 2b times the cosine of 2t. And the sines are minus 4b. Let's see, minus 4b and minus 6b might make minus 10b. That takes care of this and this. And then I've got minus 2a. Sine 2t. Oh, the sign is on the outside of parentheses. Okay, now this is equal to the desired right-hand side, 12 cosine 2t. And if I haven't botched up the arithmetic, then we've got a system of equations sitting here. The cosine term is minus 10a plus 2b for a coefficient, and that must add up to 12. And the sine part is minus 2a minus 10b. And that must add up to 0 because the original does not have a sine term. Well, just because we can, maybe we'll do this one with technology. Actually, that 2 by 2 is not too awful to do otherwise, but let's see. Matrix. We want to edit this matrix. This will be a 2 by 3, And we have minus 10a followed by 2b equals 12, and minus 2a minus 10b equals 0. So we want the row reduced echelon form of A. Oh, okay. And we'll have to switch that to, whoops, have to switch that to fractions. Oh yeah, it does come out. Not too awful. So A is equal to minus 15 over 13. And B is equal to 3 over 13. So that tells me that YP is equal to, now I called A the coefficient on cosine. So minus 15 13ths cosine 2t plus 3 13ths sine of 2t. And the general solution to the ODE is this one, the YP, minus 15 over 13 cosine 2t, plus 3 over 13 sine 2t, plus C1 e to the minus 3t, plus C2 e to the plus 2t. And that's our general solution. I'm inclined to agree. Jeffrey let out a big sigh here. Yeah. A point well taken. Now, I'm actually tonight going to show you yet another way to solve this one, which involves quite a bit less algebra and arithmetic. But it also involves complex numbers. So, you know, it's kind of a trade-off. But after you do it a few times, it's, I think you'll see that it's really better for this sort of thing. The problem is it's very limited. It only works with the single sine or cosine term on the right-hand side. Okay, well, what else could we have? Polynomials are easy to guess. Exponentials are easy to guess. Sine and or cosine, you can guess the general form pretty easily. It can be quite messy to come up with the details, but we can do it. I suppose you could have sinh and cosh for the same reason. The derivative of sinh is cosh and the derivative of cosh is sinh. So you could do, if you had sinh or cosh on the right-hand side, or both, you could do just exactly what we did here with sine and cosine. The only thing is that you never get negatives when you're taking derivatives. So everything else looks the same. And that's all that comes to mind right now. I think those are the classes of equations we need, right-hand sides we need to talk about. But I put them in a table here in the handout, so you can look them up. Yeah, if you have sine or cosine, you can guess that you need both the sine and cosine, and this thing we plug in, we call that the trial solution. Put those in the trial solution. Sinh or cosh, same thing. Polynomial of degree n, same thing. You guess a polynomial of degree n. Exponential, you guess the same kind of exponential. A polynomial times an exponential works the same way, and a sine or cosine times an exponential works the same way too, but they get really messy. So let me at least set one up I'm going to call this example 4, and I'm only leaving a little space for it because I don't plan to really solve the whole thing. It'll take too long to do that. But suppose we have this, y double prime plus y prime minus 6y equals, oh, how about this? 3t minus 5 times e to the, as long as I don't hit minus 3t or 2t, I'm good. So e to the 4t. Then you would guess that the particular solution has this form. Now, if you take derivatives of a linear polynomial times an exponential, you will get back first or second degree polynomials times the same exponential, or 0th degree. You could, by taking enough derivatives, you could knock that down to a 0. So we know that the polynomial doesn't have to go above degree 1. And we know that the exponential part would have to have a 4t in it. So you would start with this. And then you'd take 2 derivatives, plug it in the left-hand side, and you would solve for a and b. And I don't know, it's probably not really worse than what we were doing before, but it's also not advancing us very much. It's the same kind of guessing that we've done before. So let me give you an example where you have to do something different. So I'll maybe just to finish this, compute yp prime, yp double prime, and substitute to find A and B. And then, you had then y equals yp plus yh, just as before. Okay, let's do one that's a little bit different. Here's what I'm going to do this time. Notice that the homogeneous solution involves e to the minus 3t and e to the 2t. I'm going to pick one of those to put on the right-hand side. And that is actually going to cause a new kind of a problem that we haven't dealt with before. Fortunately, it turns out that there's a pretty easy trick to make it go. But if you were left to your own devices to guess it, it would be a fairly difficult problem, I think. So let's suppose we have this. Now, at this point, it becomes clear why we always want the homogeneous solution first. So we know that the homogeneous solution is C1 e to the minus 3t plus C2 e to the 2t. And that is actually a problem here, because this function, e to the minus 3t, also appears in the homogeneous solution. So let me show you what would happen if we make the wrong kind of guess here. What if we guessed that this would be yp, not yh, that the particular solution has to have the form e to the minus 3t, which we did before? Well, what you'll find out is it couldn't possibly work. And here's why. Yp prime equals minus 3a e to the minus 3t, and yp double prime equals, well, we get another minus 3, so 9a e to the minus 3t. And now we plug these in, y double prime plus y prime minus 6y equals, okay, yp double prime, 9a e to the minus 3t, yp prime minus 3a e to the minus 3t, and then we have minus 6 times a e to the minus 3t. And that, well, 9 minus 3 minus 6 turns out to be the 0 function. So, didn't work. Makes absolutely no difference what you choose a to be. If e to the minus 3t times a is just going to generate a 0 on the right-hand side. And one way people express that is they say this thing is a linear operator. The linear operator on y, which is y double prime plus y minus 6y, that linear operator is an annihilator of e to the minus 3t. What it means is it turns that into the 0 function. So that will not make a solution to this, will not make a particular solution to this ODE, because you put any of those terms in you want, they just get wiped out. They get turned into zeros. So what do you do then? Well, the answer is this. In this particular case, it will do to use AT e to the minus 3t. Now, it is possible that t e to the minus 3t could also be annihilated by the left-hand side. If that would come from having e to the minus 3t appear twice in the homogeneous solution, that would be case 2, the repeated real root of the first order linear equations with constant coefficients. So that would be C1 e to the minus 3t plus C2t e to the minus 3t. So then you just take one more power of t squared will escape from this annihilator. So you use the minimum power of t that will do, or if you're working with x, it's the minimum power of x that will do. So it's either, for second order equations, either going to be 1 or 2. And 1 will do in this case. It is messier though, unfortunately. Yp prime is, well, now we have a product rule. So we have the derivative of at is a, e to the minus 3t, and the derivative of e to the minus 3t is minus 3, e to the minus 3t, so the t down here survives. And then when you take the second derivative, you grow yet another term. So taking one more derivative here, we get minus 3a e to the minus 3t. And now we have product rule here. So minus 3a e to the minus 3t, taking the derivative on the linear part. And then when I take a derivative on e to the minus 3t, I get another factor of minus 3. So plus 9, a t e to the minus 3t. Whew. Now, it's probably worth noticing that this will compact a little bit. Minus 3a and minus 3a go together as minus 6a. So y double prime term, minus 6a e to the minus 3t plus 9a t e to the minus 3t. That's the second derivative part. Plus the first derivative, plus a e to the minus 3t, minus 3at e to the minus 3t. And then we have the minus 6 times the trial solution, at e to the minus 3t. Okay, let's clean that up. First of all, absolutely everything has an a e to the minus 3t. So no, it doesn't. Well, it does, but let's not get too aggressive with our factoring here. E to the minus 3t might as well go out. The constant terms are these. I've got minus 6a. That has a t in it, plus a. That has a t in it, and that has a t in it. Plus, now the t terms. 9at minus 3at minus 6at e to the minus 3t. And I should squeeze that in down there. And all this has to add up to, way back at the beginning, 6 e to the minus 3t. So now, by wonderful good luck, 9 minus 3 minus 6 happens to be equal to 0, right? So this whole thing just, well, not drawing it too well. All three terms scratch out to 0. And so we're left with minus 6 plus 1 minus 5a is equal to 6, so that a is equal to minus 6/5. And that means yp must be equal to minus 6/5 t e to the minus 3t. And then we can write down our general solution. It's the particular solution plus the linear combination of basis functions for the homogeneous equation. As usual, yp plus c1y1 plus c2y2. So there we go, we got it. And this is what you always do. If you're the natural choice for the trial solution collides with the homogeneous equation, you multiply it by the independent variable x or t. If that still collides with the homogeneous solution, you multiply it by another t or x. And by that point, it can't with the second order equation. You're outside with that. So then you just carry on as we have before. And that is what this handout says. It says to get started, basically you take the same class of function for your trial solution that you start with, being aware that sometimes things will get added. If you started with just a sine, you'd have to have both a sine and a cosine term for the trial solution. If you started with just a cosine, you have to still have both a sine and a cosine. And similarly for sinh and cosh and polynomials, you start with the same degree that appears on the right-hand side with undetermined coefficients. Exponentials work nicely, and products of polynomials or sine and cosine with exponentials work the same way. Then the first complication that could come along is this: what do you do if the trial solution lands inside of the homogeneous solution? You just multiply it by the minimum power of x or t to get outside of that. And then you carry on as usual. The last complication that could occur uses what we call the superposition principle. What if you had a bunch of right-hand sides, or even two for that matter? Well, it turns out you can just do them separately. And that's the beauty of these equations being linear. In other words, if I put in a y1 and run it through here, it's going to generate one right-hand side. If I put a y2 in here, it will generate its own right-hand side, and those two will not interact. So if I wanted to do this one, which will look like a true killer equation, y double prime plus y prime minus 6y equals, and now I do need to be careful how I choose, because I don't want to be here all night working it out. Suppose I set this equal to 6 e to the minus 3t, which is by no means random. That's the one we just did, right? Plus, well, what else do we do? I better keep these labeled, I'll be lost soon. Plus 12 cosine 2t plus 6x squared minus 2x. How would I solve this? Well, the answer is I would do these one at a time. And we have done them already one at a time. So solve with right-hand side 6e to the minus 3t. This will generate some particular solution, I'll call it yp1. And then you solve again with right-hand side 12 cosine 2t. And this will generate a new particular solution, I'll call it yp2. And then you solve a third time with the right-hand side 6x squared minus 2x, and that will generate yet another particular solution, I'll call it yp3. But these are the ones we've already done, so we know what those are. So the general solution, yp1, we know already. We did that once, way back. Oh, that was the one that collided with the homogeneous solution. So here it is. We solved this and we found out that yp is minus 6/5 t e to the minus 3t. And we did the 12 cosine t, 2t rather, here, and we found out that the solution is kind of messy, minus 15/13. And we did the 6x squared minus 2x here. And we got this solution, it's minus x squared minus a third. All of those were done previously. And so the general solution is this. You just stack up these particular solutions. Minus 6/5 t e to the minus 3t minus 15/13 cosine 2t plus 3/13 sine of 2t minus, oh, that was x's instead of t's. Oh, look at that. T. I should have t's there. Minus t squared minus 1/3 plus the general solution to the homogeneous equation, c1 e to the minus 3t plus c2 e to the plus 2t. And there you go, we have the general solution. Now, this would take a good long time to solve. You just, if you just started with this thing for the first step, right? As a matter of fact, it took us just about an hour. So, but it can be done. Not with joy, perhaps, but it can be done. All right. And that's it. You have learned all there is to know about the method of undetermined coefficients. I'm really trying to get to the first page here. Here it is. The non-homogeneous equations, how do you solve? Well, sometimes you can use the method of undetermined coefficients. Notice it's for constant coefficient equations. So a reasonable person might be thinking, you know, those are pretty special. If you had nothing more complicated than putting in an X or a T right there next to that A, we couldn't do it with this method. And you'd be right, we couldn't do it with this method. Unless we could, you know, we might be able to sort of invent our own method along the way. Oh, this is another special case. I can still see what the particular solution must look like. If you can guess that, then you could use this technique, but otherwise, no. All right, any questions? Next chapter. Okay, method of complex exponentials. Now, method of complex exponentials is a much smaller topic than the one we just did. We're still with this thing right here. Suppose you have a second order linear, constant coefficient, ordinary differential equation. And now we're going to say this. What if you are dealing with a single cosine or sine term on the right-hand side? And we did that with an example already. I keep throwing these down in a absent-minded sort of way, and I have to go back and finding them. We did this already, right here, this one. And we found the solution. It's kind of messy, but we found it. Now, it turns out there's an easier way of doing it, and that's what the method of complex exponentials is about. So here's the method, and I will actually, I think the first one we did was with a minus or plus 5t. I don't remember which one it was. It was minus 5t. So let's reproduce this one. And I'm going to do it, though, by the method of complex exponentials. Y double prime plus y prime minus 6y equals 21 e to the minus 5t. My goal here is to find a particular solution for this equation. Now, what I'm going to do is work with complex functions. And I got to start with this reminder. E to the I theta is cosine theta plus I sine theta. Now, I'm going to try to keep the discussion here fairly snappy so that it doesn't get, well, first of all, so it doesn't take too long, but also so it doesn't get too boring from all the miscellaneous stuff I might say along the way. But we do need to be able to work with complex numbers in order to do this. So let me just say a couple of things about complex numbers in general first, and then I'll come back to this here. First of all, if I have a couple of complex numbers and I want to add or subtract them, they are, after all, polynomials. It's a polynomial of degree 1 in the variable. You could think of it as the variable I, except it isn't variable, it's fixed, right? So adding or subtracting, you just do it as if it were an x here. So we got 3 minus 5 is minus 2, and I've got 2 minus a minus 7 is plus 5, I, and you know, that looks like high school algebra, except I've got I instead of x, right? Now, what if we wanted to multiply these? Well, probably, I'm hoping anyway, you have done this before. And what you do is, once again, you just treat it as if it were an x, except we'll get some simplification for the last step. So I'm going to take this times this. 3 times 5 is 15. Then I'm going to take my middle terms. This times this, 10i plus 10i. And this one, 7 times 3 minus 21i. And then I'm going to take this product. Let's see, 2 times minus 7 minus 14 I squared. But what is I equal to? What are we using that symbol to mean? So I squared must be minus 1, right? So that means this one simplifies. This right here, 14i squared, that is minus 14. So I've got minus a minus 14 plus 14. 14 and 15, 29 plus, and then these two will go together as well. 10i minus 21i is minus 11i. So if you're going to multiply these things out, and that got so messy, I'm inclined to do another one. You just multiply them out like polynomials. 3 times 1 is 3. Now we know actually ahead of time, the term without I is going to come from here, and it's also going to come from here. So it's going to be 2 times 3 of 6. And we got one minus here, and we got another minus from the I squared. 3 plus 6, and then the middle terms will give the i's. Minus 2i and 9i. And therefore, this is 9 plus 7i. Okay? So multiply them out like first degree polynomials, and then simplify the I squared, add everything up, and you'll get something of this form. Some feedback would be helpful. Is this simple, hard, obvious? It's okay. All right.
Where did we get the coefficients from?
Oh, I just made these up.
Oh, okay.
Yeah, these are just examples.
Yeah.
Because we're going to end up doing this when we solve this equation.
Okay.
Okay, so I want to make sure we're all together in that. All right, now what if we had this, 3 minus 2i, and we wanted to divide, say, by 1 plus 3i? Well, that's the one that occasionally, well, maybe every single time I've ever taught this course, there's some people in the class, maybe most people in the class, don't know what to do. And the answer is you multiply the top and the bottom by the complex conjugate of the denominator. So this is 1 plus 3i, you multiply up and down by 1 minus 3i. Had this been 1 minus 3i, then we'd multiply up and down by 1 plus 3i. And then we just do what we did before. What is this product? Well, this times this is 1, and then I'm going to get minus 9i squared, that's plus 9, and the middle terms are going to add out, plus 3i and minus 3i. So 1 plus 9, it always, by the way, happens that way. This squared plus this squared, 1 plus 9 in the bottom. And on the top, you know, you probably just have to multiply it out and see what you get. The real part is going to be this. 3 times 1 is 3. This times this is minus 6. Middle terms, minus 2i. And minus 9i. So I've got 3 minus 6, negative 3 over 10. And 9, minus 9 and minus 2 is minus 11. Minus 11 over 10i. Okay, so you multiply top and bottom by the conjugate of the denominator, simplify, and you're done. And we're actually going to get some practice in that here in a bit. Okay, so now when we write down a complex number, it's like sort of X is the go-to variable for real numbers. Z is generally indicating that we have a complex number in mind. So if Z is A plus BI, there's two functions you need to know about. The real part of Z is A, and the imaginary part of Z, this is a confusing name, because a reasonable person, I would say, if you just showed them this, A plus BI, what's the imaginary part? BI, right? But no, it's defined to be B, the coefficient on the I. So REZ is the real number part of A plus BI, and IMZ is the coefficient of the imaginary part. Now, let's get back to where we were and saying, suppose that y equals e to the I theta. Well, that's cosine theta plus I sine theta. So if you took the real part of y, you would get cosine theta. And if you took the imaginary part of y, you would get sine theta. And it turns out that is pretty handy for solving equations. If we have a sine or cosine on the right-hand side, it is far easier to replace it by a complex exponential, solve that system, and then take the real or imaginary part, depending on whether you had a sine or cosine to begin with. So rather than try to explain in the abstract, I will just do a couple, and you'll see what to do. Y double prime plus y minus 6y minus 6, try again. Y double prime plus y prime minus 6y equals 21e to the minus 5t. Now, it's critical that this not land in the homogeneous solution, but it doesn't. Those are e to the minus 3t and e to the 2t. So what I'm going to do is you think of this as injecting it into the complex plane. Oh, what am I doing here? I'm so sorry. I started with the wrong one. Well, I'll just fix it. Let's make this cosine minus 5t, okay? Then everything else will be fine. So because I have cosine of minus 5t here, I use 5I theta, minus 5I theta for my, actually, we can do that, but why not think ahead? The cosine is an even function, right? Cosine of minus 5t and cosine of 5t are the same. So why on earth would we carry around that negative sign for no profit? It's exactly the same equation this way. So ignore the minus. We don't need it. Okay, now what I'm going to do is this. I'm going to say, okay, now I'm back to the exponential case. It's just that it's complex. So I know that z, the particular solution for the complex equation, has to look like this: some constant times e to the 5I theta. And I can easily write down first and second derivatives now. 5I is the chain rule factor. And the second derivative, well, it's going to be the same thing. I just pick up another 5I. So I've got 5 squared I squared, that's minus 25. Okay, so there's my derivatives, and I'm ready to write this down. Z double prime plus Z prime minus 6Z equals, all right, Z double prime is minus 25, and you might notice absolutely everything has a k and an e to the 5it. So I'll leave that to the end. Minus 25 plus y prime, or z prime in this case, 5i minus 6 k e to the 5i. Why did I change the theta? I don't know. I guess it doesn't hurt. And that's supposed to end up being 21 e to the 5i theta. So this needs to simplify a little bit here, right? Minus 31, good grief. That's a mess. I'm just double checking to make sure I've got the numbers I should have. What's right? Okay, so my equation says this. I've got k e to the 5i theta on both sides, right? So no, I've got e to the 5i theta on both sides. So I've got something times k. That something is minus 31 plus 5i times k is equal to 21. And therefore k must be equal to 21 over minus 31 plus 5i. And this is why I did the review on dividing complex numbers, because now we got to do it. Okay, on the bottom, now we could just use our shortcut. We already know what's going to happen. You're going to get this squared plus this squared. 31 squared, fortunately, I have my calculator. 31 squared is 961. 5 squared is 25. And up on the top, I've got 21 times minus 31. Minus 651. This times this is 105 minus 105i. And 961 plus 25 is 986. So minus 651 over 986 minus 105 over 986i. A simple complex number. All right, so that's k. But we're essentially done now. This is what we know. ZP equals K, which is this crazy stuff, minus 651 over 986 minus 105 over 986i times e to the 5i, let's make it t in this case, e to the 5i t, which is the same number. I'll put quotation marks so I don't have to copy it all down. Cosine 5i t, well, cosine 5t plus I sine 5t. Now, we started way back here with cosine. So we want the real part. Yp is the real part of z, which is, okay, it's this number here times this number here, and they pick off the real part. Well, there's two ways to get a real part. You could take this real times this real. That's supposed to say cosine. Or you could take this imaginary times this imaginary. So it'd be this times this. So the coefficient is minus 105 over 986, but then it's multiplied by I squared, which is minus 1. So you lose the minus. Sine of 5t. And if you really are so inclined, you can take this and run it through the original equation and see if that comes out to 21 cosine of 5t. Probably not worth it. But. Now, the only thing that could be different whenever we use this is you might have a sign here on the right-hand side. Everything, if we had had the sign, every intermediate step would be exactly the same until you get to here, in which you'd say yp equals Im of Cp. And then you take the coefficient on the I. You don't keep the I. And so we should maybe do one that isn't so horrid. A couple of them, actually. So let's go back to this one that we did earlier. And we came out with a solution here. It wasn't all that nice. Minus 15 over 13 and plus 3 over 13 on cosine and sine, but better than we just had. So let's start here. Y double prime plus y prime minus 6y equals 12 cosine 2t. Switch to complex functions. Z double prime plus z prime minus 6z equals 12 e to the 2 it. All right, then we say, well, in that form, the particular solution must be just some multiple, let's call it k, of e to the 2it. And we'll need derivatives. After you do this a few times, you get to where you can skip this step, but I'll write it out for now. First derivative, you pick up a coefficient of 2i. 2ik e to the 2it. I'm not going to have room there. I might as well move down. Second derivative, well, everything out here is a constant. So you just pick up another chain rule factor, another 2i. 2i squared is minus 4. Minus 4k e to the 2it. And now we plug them into the left-hand side. Left-hand side of the equation, this left-hand side here, is z double prime minus 4k plus y prime plus 2ik minus 6 times the original function minus 6k, and every single one of them is multiplied by e to the 2it. And that we want to add up to 12 e to the 2it. Okay, let's clean this up a bit. Minus 6 and minus 4 are minus 10. Minus 10k plus 2ik, I might as well factor the minus 10 plus 2i times k is equal to 12. You can divide the e to the 2it off from both sides. So k is equal to 12 divided by minus 10 plus 2i. And now we want to simplify. You do that by multiplying by the conjugate of the denominator, minus 10 minus 2i. You just change the sign on the imaginary term. Okay, and on the top, we've got, well, we've got kind of a mess. Minus 120 minus 24i. And on the bottom, the formula is this. You're always going to get this squared plus this squared, 10 squared plus 2 squared. So 104. So k is equal to minus 120 over 104 minus 24 over 104i. And of course, these fractions will reduce. Actually, your calculator will do that for you, right? I'll do 120 divided by 104, and then I'll ask my calculator to turn that into a reduced fraction, 15/13. Looks familiar, huh? And the other one, 24 over 104. (3/13). And is that positive? That's a minus. Minus 3/13i. That's k. So now I know that the complex equation has a particular solution, which is k, 15 over 13 minus 3 over 13i times e to the 2it. But that is cosine 2t plus I sine 2t. Okay, now I had a cosine on the right-hand side. So that means yp is the real part of zp, and the real part comes this way. A real times a real, 15/13 cosine 2t. And the other way to get a real is to take an imaginary times an imaginary. The I squareds turn into -1, and that cancels this minus here, so I get plus 3/13 times the sine of 2t. And I think that's the solution we had before. Anyone want to ask a question? I'll let you cook on that while I do a near instant third example. And I do mean this one's going to go very fast. Y double prime plus y prime minus 6y equals 12 sine 2t. The only difference between this one and the one we did previously is I had a cosine, now I'm switching to sine. So replay all the steps above to here. ZP equals, it's this product right here. 15/13 minus 3/13i times cosine 2t plus I sine 2t. So everything, and I mean absolutely everything. Once you switch to z, you're going to have switched to a complex exponential on the right-hand side, And then every single step is absolutely identical until you get down to here. Then your last step will be this, yp equals, and now since we started with a sine, rather than the cosine, we're going to take the imaginary part of z. And there are two ways to get an imaginary number out of this product. You could take this imaginary times this real, minus 3/13 times cosine 2t, or you could take this real times this imaginary. So we just write those down. Minus 3/13 times the cosine of 2t. Notice I'm not copying the I. And plus 15/13 this times this sine of 2t. Now, if you think about it for a minute, we've already said that equations of this form, these ODEs, if you have a homogeneous equation, it models a mass spring system with no driving force. It also models a LRC circuit with no input signal. So if you put something on the right-hand side, like this cosine 2t or this 12 sine 2t, what you're modeling is exactly the same kind of a system like an RLC circuit with an input signal. And this solution is the signal that will be at work in the system long term. So, so sinusoids, sines and or cosines are actually very, very common inputs for both of those kind of systems, especially electronics, right? So even though this is a very narrow kind of equation you can use this technique on, it's still very valuable. And as a matter of fact, I think it's the electrical engineers are the ones that tend to use it. Jeff?
I think you lost the negative.
Oh, did I? Where?
Out of the 15/13 on the top, like for the first example too.
So you think that one should be a minus?
It was for the previous.
Oh, look here.
Yeah.
There's a minus here. Thank you. Good catch. Fortunately, it's a very easy one to fix, isn't it? So you get a minus here on this real part, and therefore a minus here. And then, of course, everything's the same. So minus 15 here. And this must be a minus then. Does it match otherwise? Yeah, okay, good. Thank you. So the big picture is you have a constant coefficient equation. Let's think of something we could do here. And you have a cosine or a sine term on the right-hand side, so constant times that. I'm going to choose a 12 because it's got a lot of factors, but it's not too big. How about this? Sine of 3t. Then the way you solve this method is, first of all, you just switch to complex form. Same coefficient. Same coefficient up in the exponent here. Then you use the same trick for ZP that we used for the undetermined coefficients. Take two derivatives. plug that into the equation. So y double prime minus 9, the k and the e to the 3it are common everywhere, plus 2y prime, 2 times 3, 6i, minus 3 times y, minus 3, all times k, e to the 3it, equals the right-hand side, 12 e to the 3it. The 3it's cancel out, and we solve for k, 12 over whatever we have here. Minus 9, minus 3, minus 12, plus 6i. Now this one, this is begging to be reduced before you go any further, right? And you should, because you don't have to, but you're just making life hard for yourself if you don't. Divide everything by 6. 2 over minus 2 plus I. We do the division by multiplying up and down by the conjugate of the denominator. K is equal to, okay, this times this is minus 4. This times this is minus 2i. And the denominator is this squared plus this squared. 2 plus 1 is 3. So z, p, is k, which we now know, minus 4/3 minus 2/3 I, times cosine of 3t plus I sine of 3t. Okay, and we started with a sine here. So y is the imaginary part of z. And imaginary part, let's see, we could get this times this, minus 2/3 cosine 3t. Another imaginary number is this times this, minus 4/3 times the sine. And there you go. So in practice, this actually does tend to be easier than the undetermined coefficients. We do have another option, and that would be to set yp equal to a sine of 3t plus b cosine of 3t. A couple of derivatives, system of equations. This really is easier. But the other way works. There's nothing wrong with it. Okay, the next assignment is half a dozen problems of these things just exactly like this, and a half a dozen problems with the undetermined coefficients. So it's just from tonight's work, because that's all we have to work with, right? So get those done by next time if you can, and you'll be in good shape for taking a break over the long weekend. And then, of course, there'll be more stuff piling up from Thursday's lesson, but at least you won't be too far behind. Okay, I'm finished unless you all have questions. Okay. I guess that's it. I'll see you on Thursday. Linda, I corrected the records, so it's done. Okay.